In this class, we will briefly review the architecture of the 8085 microprocessor. We have already seen about the 8085 microprocessor. We will briefly review it, and then we will go to the how the data and address are demultiplexed, and afterwards we will go to the instruction sets of the processor. So, we already saw about the various registers in the microprocessor. So, the architecture of the microprocessor is shown here, and it consists of general purpose registers as you see here B, C, D, E, H, L. So, these are all 8-bit registers, and they can be used all these registers can be used as 8-bit registers, or put together. B and C can be put together, and then it can be used as a 16-bit register. Similarly, D and E can also be used together as a 16-bit register, and H and L also can be used together as a 16-bit register. So, A is the accumulator, and then of course, F, this is called as F register, which is the flag register. Okay. Then this accumulator. So, accumulator also is a 8-bit register, and in this register all the arithmetic and logic operations are done. Okay. So, it will store the 8-bit data after doing the any arithmetic or logic operation. Okay. And the input output. So, if you want to transfer data to an input output device, the data has to be transferred from the accumulator. So, the data, the 8-bit number has to be in the accumulator. From this accumulator only we can transfer anything to the input output unit. So, it is used to store 8-bit data, and also when you do any arithmetic or logic operation with a number in accumulator and another number in memory or in this register, the result will be stored in the accumulator. And if you want to transfer any data to the input output device, then necessarily it has to be from the accumulator only. Then we have the special purpose register. We have the flag register. So, the flag register again is a 8-bit register. So, each bit in this 8-bit has got a meaning. Okay. So, they are noted as S, Z, A, C and so on. So, each has got a meaning. So, what is the meaning of this S, Z, A, C, P? So, it is indicated here. X means it is not at all used. Say they are don't care. So, S means sign flag, Z 0, A, C auxiliary carry, P parity, and C Y is the carry flag. So, each bit will be set depending upon the result of the operation. So, when you do a arithmetic logic operation, you may get various results, you may get a overflow, you may get a 0. So, based on the results of the operation, the individual flag bits will be set. Okay. So, this sign this bit will be set. So, this indicates the sign of the result. So, when you use signed arithmetic, the most significant bit represents the sign bit. Okay. So, negative number is represented by the most significant bit. So, if the most significant bit is 1, then this bit will be set. So, that is when this most significant bit is 1, it indicates a negative if you use a signed arithmetic format. So, otherwise it will become 0. Okay. So, otherwise if the most significant bit is 0, this will become 0. Then you have the 0 flag. So, when you add two number, you may get 0 as the result. Okay. So, when you do a logic operation, again you may get a 0 as a result. So, if the arithmetic becomes this accumulator becomes 0, this 0 flag will be set. Okay. So, it will be set following again increment, decrement, any arithmetic operation, increment, decrement, addition, subtraction or any logic operation. When you get a 0 as a result in the accumulator, this flag will be set. Okay. So, for example, you are adding two numbers. Okay. So, add this. So, you are getting a 0 as the result. So, in that case 0 flag will be set. Okay. Then another is the carry flag. Again, when you add two binary numbers, okay, you will get a carry, that is a overflow. Okay. So, for example, you see here you are adding this number, this one binary number, this is another binary number, you are adding these two. Okay. So, you are getting the result, and then so this is the 8-bit and you are getting a carry. So, when you get a carry, this carry flag will be set. Okay. So, this carry flag will be set, that is the use of the carry flag. Then again when you subtract, so this number is smaller and this number is larger. So, when you are subtracting from a smaller number a larger number, naturally you have to borrow. So, there will be a borrow. Okay. So, when you have a borrow also, this flag will be set. So, whenever you have during addition, when you get a carry, this flag will be set, and when during subtraction when you get a borrow, again this flag will be set. Then you have the auxiliary carry flag. So, when you add two 8-bit numbers, there will be carry from the third bit, that is 0, 1, 2, 3, third bit to fourth bit. Okay. So, in such case the auxiliary flag will be set. Then you have the parity flag. So, parity bit is used so in microprocessor during data transmission. So, we use what is called as the parity check. Of course, we will see all those things later when you see about the serial interface. So, parity depends upon how many number of ones are there in a byte. Okay. So, when you after a arithmetic or logic operation, so you may get a binary number, so 8-bit. So, number of ones may be a even number, you may get a even number of ones. In total number of 8 bits, you may get even number of ones or odd number of ones. Okay. So, depending upon whether it is the total number of ones in a byte is even or odd. So, this parity bit will be set. So, this parity bit will become 1 when you get totally even number of ones. Okay. When the count is even, and when they count the number of ones, the total number of ones is a odd number, then this parity will become 0. Okay. So, now we have other special purpose registers, that is a program counter. So, program counter is a very important register. So, it is a 16-bit register. So, this program counter is the one that is responsible for sequencing the program, that is program has to all programs are there in the memory sequentially starting from say 0, 1, 2, 3 like that. So, it will be there in the memory. So, the program counter will contain the address. Okay. So, the contents of the program counter will be used to address the memory. Okay. So, the microprocessor will take the program or the instruction from the memory. So, a particular memory location from a memory location, and then it has to automatically go to the next location and so on. So, once the microprocessor takes the instruction from a location, then the program counter will be incremented, and the contents of the program counter will be sent to the address bus, and it will go take the instruction from the next location. Then, so this register will hold the address of the next instruction. Once an instruction is taken, this will be incremented, and then it will point to the address of the next instruction. Okay. So, obviously, so 85 can address 64,000 memory location, and it has got 16-bit address line. So, the address consists of 16 bits, okay, that is 2 bytes. So, obviously, it is a 16-bit register. This program counter is a 16-bit register. So, next of course, again another 16-bit register is a stack pointer. Okay. So, we saw that this is the stack pointer. So, we have another 16-bit register which is a stack pointer. So, the stack pointer also contains address. Okay. The stack pointer also contains address. So, while you are running a process, so there may be some important data which you may have to store it in the memory and then access it later. So, you have to allocate some memory location which will not be normally used by the other programs or other data. So, normally top of the memory location will be generally free. For example, in a computer, suppose in a hard disk you have 250 GB hard disk. So, you may not use the entire disk, then the the higher side of the disk will be generally free. So, like that in a memory, semiconductor memory, so microprocessor uses semiconductor memory. So, in semiconductor memory also, so you may have 4 kilobyte, 8 kilobyte and so on, depending upon your application. You may use memories of the order of few kilobytes or 8 kilobyte and so on. So, in that memory you may not use the entire thing. So, normally the top of the memory, that is the higher side of the memory, will be generally free. So, the stack pointer will be initialized to point to the top of the memory. Okay. So, it will start from the highest location of the memory, and as it stores the it will point to the next lower address. Okay. So, program counter will keep on incrementing and pointing. Once it takes the data from the memory, it will point to the next higher memory. Okay. So, but in the stack pointer, this will point the highest memory, and then again from high it will be coming down. Okay. So, this area is called as the stack, where we store some important data when you are doing some operations, so when you are doing some process. Okay. So, that area is called as a stack. Okay. So, this important data may be required for us when you are solving some problem Okay. So, microprocessor is programmed to solve some problems, this data may be required and it may be, so you have to write a program to retrieve it. So, it will be retrieved. Okay. So, it will store from the top, okay, starting from the top. So, let us say this is bottom and this is top. So, it will store from the top, then again next it will store like this, like this, like this, like this, it will come, and then whatever that is stored again it will be retrieved again in this fashion. Okay. So, it will store like this and then it will retrieve it like this. Okay. Then we have other registers which are not there is no instruction to access these registers. So, they are used for the internal operation. So, there is what is called the instruction registers. So, when you fetch an instruction it will be stored in the instruction register which and then it will be decoded by the decoder, and then according to the instruction action will be taken. And then the microprocessor also has got a clock generator. So, of course 3.12 megahertz or nowadays it can operate even at 6.25 megahertz. Okay. So, now let us see about the address and the data bus. Okay. So, the microprocessor 8085 microprocessor is a 8-bit processor. So, obviously and then it can address up to 64,000 memory location. So, to address 64,000 memory location you require a 16-bit number, that means you require a address of 16-bit. So, the microprocessor has to have a address pins of 16 pins for address it is required, and then data you have to have 8-bit. So, the microprocessor has to have a 8-bit or 8 pin as data. Okay. So, 16 plus 8. So, it requires 24 pins. So, that will make the size of the microprocessor larger, okay, because you have to have so many pins means obviously the size will become large. So, what Intel has done is it uses multiplexing, that is same pin is used for address as well as data as you see here. So, although it requires 24 pins. Okay. So, the microprocessor here, so address requires 16 pins. So, it has got only 16 pins. So, you have 8 pins here. So, you have 8. So, AD0 to AD7, that means you have 8 pins here. So, representing AD0, AD1, 2, 3, 7 and then again another 8 pins. Okay. So, these 8 pins will be shared by address as well as the data. Okay. Same pin is shared. Okay. So, this is called as multiplexing. Okay. So, this will send data as well as the address. However, external devices has to recognize whatever you get as data or as address. So, we use what is called as the arithmetic address latch enabled. So, we use what is called as address latch enabled and a latch to distinguish that. So, we will now again continue with the study of the address and the data bus system. Okay. So, here you please see this unidirectional. So, the address bus or unidirectional means the address will be sent by the microprocessor to the external units, that is you see the arrow in this direction. So, it is unidirectional, and then you have the data. So, this you have the address as well as the data. Okay. So, the data will be bidirectional. So, this can for data this can receive the data as well as it can send the data. Okay. So, these 8 lines are bidirectional. Okay. So, these 8 lines are bidirectional, that means data can go like this and then data can come like that is the meaning of the bidirectional. Okay. So, during of course execution of the instruction. Okay. So, the microprocessor carries 8 data bits as well as the address bits. So, first you have to send the address. So, these pins will first send the address, okay, and these pins also will send the address. Okay. So, when the address is present, there will be a pulse from this address latch enabled. So, which will store the address. Okay. So, this 8 bits it will be stored and that will go as address. Then this pin will not send the address, it will pins will send only the data. Okay. So, these pins will send only the data and this will go to the data pins of the memory or output units and so on. Okay. So, you have to separate the address and then the data. So, you have what is called as this a latch, which is a latch is nothing but a memory. So, it is a 8-bit memory. So, this 8-bit memory will be triggered by this address latch enable pulse and then it will store it, and after it has stored, these pins will send the data only and the data will come like this. So, now that will be clear when you see the timing diagram. Okay. So, you can see the clock pulses. So, these are called as a clock. Okay. So, the microprocessor is driven by a clock generator. So, when you see it on the oscilloscope, you will it will be like this. Okay. So, you can see, so this is this color. So, this yellow color is the address and this is the data. Yeah. So, during the first clock pulse, so you are getting the, so these are the, so what you are getting in these pins and what you are getting in these pins, and what you are getting in these pins are shown as a timing diagram. So, in this pins you are getting address. So, during the clock, first clock period you are getting the address. So, these pins and these pins are sending the address. Okay. So, the address is continuously available in these lines. Okay. Address is continuously available as you see here, but in this line address is not available. Address is available only during the first clock pulse. Okay. Only during the first clock pulse address is available. So, then afterwards address goes off and data comes. So, when the address is available, that address has to be captured. Okay. So, unless you capture this address, then it will not be available at all. Okay. So, you have to capture the address. So, what you are getting? You are getting what is called as the address latch enabled pulse. So, during the first clock period, when this address is available, you are getting a address latch enabled pulse during the first clock period. So, this address latch enabled pulse will capture this address. So, this will capture this address on this latch. So, this is now captured and hence it is now available here. Okay. So, although it goes off, now it has been captured by this latch and it is now available in this as at the output here. Okay. So, it is now available. Then this bus will not send the address, as you see here, address will not be sent, it has gone, and then data will come. Okay. Then data will come. So, although data is here and no address is there, but it address has already been captured. So, the address is available. So, A0 to A7 and A8 to A15 together are available at this. So, in these lines, so in this bus both are available together, because this has been already captured by this latch. Okay. And both together, this and this are available even here. Okay. And then data will come through these lines, and it may go to the RAM, ROM or any IO unit. Okay. So, that is working of this demultiplexer. So, this is called as the higher order address and this is called as the lower order address. So, the higher order address is fully present for all the 3 clocks. So, this is one machine cycle, this is called as one machine cycle. So, all throughout this 3 clock periods, this higher order address is available, but the lower order address is available only for 1 clock period, but it will be captured by this latch with the help of the address latch enabled signal, and it will be stored here, and then both are available of course. Okay. And this bus will be used for data. Okay. So, after this has been captured, this bus will be used for data. Okay. So, this is again same thing drawn in a bigger scale. So, now it will be more clear to you. So, higher order address available throughout. Okay. And then lower order address available only for 1 clock period, and then this address latch enabled pulse captures this lower order address, and once it has been captured, the address lines will be released for data, and then data is now available. Okay. So, you can see here. So, this is the higher order address bits. Okay. So, this is the lower order address bit, and then address latch enabled pulse will capture this address during the first clock period, that is T1. Okay. Now, let us see about the instructions of 8085 microprocessor. So, we saw the architecture of the 8085 microprocessor, what are the registers, okay, general purpose registers and then a special purpose register, and we also briefly saw the hardware of the microprocessor. Okay. So, we saw the pin details, that is how all the 40 pins and what are the various pins, and then the external connection also we saw, that is how to reduce the number of pins and keep it within 40, how the Intel shares the pins between data and then address. Okay, because the most of the pins will be taken by data and then the address in any microprocessor, because you require for a 8-bit processor you require 16 address lines, and then of course another 8 data lines. Okay. So, most of the pins will be taken over by these address and data lines. So, to keep the size minimum, that is within the 40 pins. So, we use time sharing. Okay. So, which is called as the multiplexing. So, how it is done we saw. Now, we will see about the instructions of the various instructions available with the 8085 microprocessor. Okay. So, it is 8-bit microprocessor, and so instructions are given in the form of a binary code. Okay. So, microprocessor cannot understand any language, it can understand only binary numbers. So, the instructions are given in the form of a binary code, that is a 8-bit binary code. So, it is a 8-bit processor. Obviously, you can have 250 combinations. So, see here you can have 250 combinations with 8-bit. So, it is possible to have 256 instruction, but we use only 246 instructions, okay, with all the combinations. So, but the basic instructions are only 74, and then combinations of all the instruction, everything works out to 246. So, basic instruction, okay, example move is a basic instruction which moves data. Okay. So, in that there are several combinations, okay, move A comma B. So, we can, another combination is move B comma E, and then another combination we can write move D comma H, like that. So, like that in the same instruction we have several combinations. So, this basic instruction we have 74, and several combinations of this instruction, everything put together we have 246 instructions. So, we can group. So, although there are 246 instructions, it is very easy to, you should not be afraid that 246 instruction how to study. It is very easy to study, because it can be grouped into very small group only. Okay. So, we have data transfer instruction or a data transfer operation, instruction for data transfer, and instruction for arithmetic operation, and we have instruction for logic operation, and the instruction for branch operation, and then instruction for machine control operation. So, we have grouped it into 1, 2, 3, 4, 5. So, they can be grouped into only 5. Okay. So, although 246 it may look that a big number, but actually they can be grouped into only 5 group, and it is very easy to study them. Okay. So, we will see them one by one, and before we see about all these things, we will see the format of the instruction. Okay. So, each instruction has got 2 parts. Okay. So, it has got first part. So, an instruction has to perform an operation on some number. Okay. So, it has to tell what operation you have to do, and then it has to tell about the data also. Okay. Say for example, so that operation part, so the part which tells about the operation is called as opcode. Okay. Opcode means operation code. So, op, okay, and then code. Okay. So, this is called as the opcode, and the second part may represent the data which it has to operate on. Okay. So, that is called as the operand. Okay. So, if we see the example, it will be very clear. So, you have to do some operation, you have to do a operation of moving. Okay. So, this expansion of this is move immediate. So, some movement of data to a register, that is a operation. Then you have to mention the data also. So, this data has to be moved to this register. So, this is the operation that has to be performed, that is you have to move a data to a register. And what data? Data is 4F, this is binary 8-bit number, you have to represent it in hexadecimal form. So, H means hexadecimal. So, 4F is the operand. So, it has to obviously, this is the opcode and this is the operand. So, the instruction consists of an opcode and then an operand. Okay. Now, let us see about the various types of instructions. So, the data transfer instructions. So, the data transfer instruction basically it copies data from a source to a destination, copying of the data from a source to a destination. So, some of the examples of the data transfer instruction. So, MOV means move. So, this is a shorthand. So, these are called as mnemonic. Okay. So, every time we cannot be write move as MOVE. Okay. So, you have to shorten it. So, Intel has introduced this type of notations which is called as mnemonic, and then MOV means move, moving a data, then move again moving a data, immediate data, I move immediate, and then loading a accumulator, A means accumulator, loading, and then storing, use store ST, like that. Okay. So, these are some of the data transfer operation opcodes for data transfer operation. Okay. So, data can be transferred between registers and between register to memory location, and then memory location to register, and then IO devices to the accumulator. So, these are the various types of data transfer. You can transfer data from one register to another register, from a memory location to register, from a register to memory location, and then you can also transfer data to a input output device. So, to transfer data to a input out device, you can transfer it only from the accumulator, not from any register or any other register or memory, but the input output data transfer can take place only between accumulator and then the input output port. Okay. So, let us now see the summary of what you have seen so far. So, we saw briefly about the architecture of the 8085 processor, and then we saw how the address and data are multiplexed. So, to save the number of pins, we are using the address latch enable signal to share the same pins for data as well as for address. And then we went to the other topic, that is the instruction sets of 8085. So, we saw how the instructions are grouped, what are the various data transfer, arithmetic and logic, branch and machine control. Okay. So, these groupings we saw, and then we started with the data transfer instructions. Okay. So, in the coming class we will see more about these various instruction sets. So, now I will ask you some a few questions. You kindly find answer to these questions. So, question number 1. So, when the carry flag will be set? Okay. Then question number 2. So, what is the use of the parity flag? Then question number 3. What is the function of the address latch enabled, that is ALE signal? Then question number 4. Mention the various types of 8085 instructions. So, with this we have come to the end of this session. Thank you very much.